But Thompson, I'll start this off by reviewing a little bit of what we have here on the title page. We're going to be talking about materials, and the concept here is to integrate all of the elements that we have here in this circular here on the left of this title page of materials, how that can be converted into risk assessments. We're obviously embedding that risk assessment information, cycle assessment, and of course the bottom priority for the whole process here is to users to have more sustainability products and be in controls. So the context here is that this is all related to demonstrate here to you how we have been able to accomplish that. So the next chart.
All right, within the hour, we'll review what motivated us to develop a practical working model versus focusing on a theoretical framework. Our research on past attempts to integrate the two disciplines, of the various data and application layers and components of LCAS today, and then we'll move right into the actual findings, data gaps, etc., and then end with challenges, conclusions, and next steps. We're starting this project. Our goal was really to improve data quality and to reduce uncertainty and basically answer the question for our clients. What we were finding is that we were having our clients ask us quite a bit regarding the information for them, so that organizations such as the USGBC. So we wanted to expand on this information and get more meaningful information. What we're not trying to with this project is we're not trying to, this is interesting. What we're not trying to do is we're not trying to evaluate the environmental impacts of risk associated with not producing particle board and redirecting the shavings or into landfill or incineration. We're not trying to conduct a comparative analysis of software tools or methodologies, or we're not trying to discourage the use of one method or another. We simply started this project, again, to improve the quality of data for the end user. When we talk about combining risk and life cycle, there are going to be instances when conducting an LCA by itself is adequate, or a risk assessment is going to be adequate. But when you think of the two, depending on which discipline you come from, I always think that life cycle assessment can inform, a risk assessment biologist would say, okay, life cycle thinking can inform the conduct of risk assessment, but I think of it from once we do a life cycle assessment and we identify that there is a potential for risk, that a risk assessment will also be able to influence the next steps after you've conducted a life cycle assessment. We're going to be able to obviously via life cycle indicate whether we need more detailed evaluation, and some of the past approaches that we investigated did highlight limitations that to sustainable development that happened later on when these two studies weren't conducted at the product development stage. When we talk about combining risk and life cycle assessment, again, this is from an LCA practitioner's point of view. What happens here is, from my perspective, LCA would identify the potential for risk. As it's not able to provide risk analysis with detailed information on any chemical form and location, it's very difficult for an LCA to do anything except conclude that what we use less, if we decide to make a change based upon this box at the top, we can only conclude that less is better because it is a mass-based system. We can't really tell if the alternative would be if more air emissions were better, or if it were better if we kept the emissions to water. We also don't have any threshold for toxicity. So this is where risk assessment comes in and fills in those data gaps. Interesting. Okay. Okay, George?
Yeah, the common attributes that we found is Rebecca comes from a life cycle assessment background, and I come from a toxicology risk assessment background. And as we began to communicate over the past several months, we found that there were common attributes between us, and that is that both fields have structured evaluations. There's more qualitative, there are qualitative but also quantitative capabilities in it, and the risk assessment in particular enables to do comparative analyses of different chemicals, raw materials, processes, etc. And so the context here was to look at the screening assessment capabilities in both assessment methodologies so that we could prioritize the concerns that would be the bottom line in the assessments.
When we did our literature review for what had already, what we found is integration strategies were focused on fast and easy, and also aggregated population-based data, such as the EIO-LCA data that's available from Carmel or the toxic release inventory, and they were still concluding that it was something that that would still be based upon broad-based assumptions and normalized average data. So we still weren't accounting for site and application-specific risks, which are really making materials in the building product sector. George?
So the methodologies that we used in this embedding process was to quantify the direct health impacts, but do it across the life cycle of Particleboard. And we simply chose Particleboard because we had the data available on that from a risk perspective. We also have the popular foam, and we have several other products, but it can be used against any product. But Particleboard is the one that we've selected for as the example in this presentation today. We're looking to integrate then the lifecycle assessment procedures with the risk, the bottom line focus, and we're using the idea of a single panel of Particleboard weighing about 30 kilograms from a LCA quantitation perspective. And the primary focus then are some things that are used to make the Particleboard, to bind it together into, and what are the emissions from those the entire life cycle.
Okay, now when we started to look at what an integrated analysis would look like, we decided to keep it simple. We weren't going to attempt to build an integration data layer, for example. We weren't going to make any software, application software, build any subroutines or anything like that to tighter integration, but keeping the two, we kept the two tools separate. Decided we were going to see what we got and then fill in the gaps. The risk collection focused on a concentration-based for each chemical constituent. I took those concentrations and converted it to a mass-based inventory. Then we used the use tox impact assessment method because it does have a risk component built into its methodology. I also wanted to see what a gap analysis, the gaps we were trying to fill current assessment systems that are already being used by the communities, such as that are already out there, such as by the USGBC and other ranking organizations. George?
So once we have inherent gaps in the LCIA, then we wanted to see if applying GreenSuite risk assessment entire life cycle could help fill those gaps. In the manufacturing, in the earliest stage of Particleboard, formaldehyde is one of the early reactants, and so that was the focus as to what happened to the concerns with formaldehyde across the life cycle. And so we were trying to, by merging our capabilities together, then the question was, fill the data gaps that were inherent by doing either by themselves. And then, of course, can we show that there is an added value if we combine assessments?
Okay, so in terms of the scope for this project, the areas that are highlighted in orange, what it came down to is we had to narrow our focus to a single chemical constituent. Even though we built the whole LCA and the whole risk assessment out for all of the chemical constituents, we kept it focused to the incoming chemical reactants for this generic resin CR component that would be in manufacturing, and then how these incoming reactants, as they travel down through the life, what those impacts look like from a risk perspective. George?
This chart shows reactants, and it's very small print here, but let me simply say to you, the 4 lines here, the 4 primary lines are the different resins, but inside of each of those are the chemical quantities that were used to make that resin. This shows reactants. As indicated in our presentation is going to use the resin CR as our example, but we did the analyses on each of the materials here. So we did it on each of the 4 formulations on the side. Outgoing side, we have 6 different reactants here. With the top, again, the generic resin CR, generic OR, and ending down at the bottom with the wax emulsion. These formulations, but all of these formulations were analyzed individually, as were the individual chemicals. But the one you're going to see us go through on a consistent, again, the generic in the input, and we're doing the output, and in the output, the finished Particleboard is actually composed of constituent pieces, the resin, the wood at the top, the resins, and then acid sulfate in the middle, and the wax emulsion at the bottom.
Okay, now keep in mind this isn't an all-inclusive list. From the health and safety perspective for what used by building products, materials, what they're saying for the environmental side is everybody at lead credit needs to produce based on LCA. And then from the health perspective, the next 3 bullets, the Quartz project, the HPD collaborative, and Google's Healthy Material Assessments tool, are all based on a and then the ACC just in February, a statement, I haven't seen a standard. And then in terms of I did just get an email this morning about Pharos incorporating Create tool. However, that still is a hazard and point-based chemical screen. So we could still say that the current tools out there right now are hazard-based. Now, when we look at the left column here, these are what's going on in terms of building products, the criteria that's available today. You're looking at aggregated impacts, hazard-only based assessment, mainly because the EPD isn't this is a check mark here, because the EPD, they're not using the use tox health, they're using what's available from Quartz, the HPD collaborative, Portico, and now Pharos with Cradle to Cradle. And there's a total lack of data at the product installation and use phases. So the question comes down to, how do you fill in the missing pieces to supply these building manufacturers and their clients with information relevant across the entire life cycle? George?
So paradigms that are available to do building material selection. There are 3 different paradigms. Go through these, and this, even after the presentation, you can look across as well in this layout. The first paradigm is hazard only comparison, and those are some of the items talked about here, that there are a small number of endpoints. There are 5 and 4 endpoints for chronic health in most of those typical systems, and they do it benchmarking. So if there's a benchmark of a 1 highly hazardous material, then you're in a building. But any sensitivity in that particular group. If you move a use of any specific endpoints, it talks about non-cancer and aggregated effects, and of course uses factors. The LCA with use talks does not include dermal exposure factors at all considered in the LCA analysis, because the GreenSuite risk assessment in total of 17 different endpoints, 8 for acute and 9 for chronic, quantitative on a scale of score, and 100% is a best score, and among those 5 that are dermal exposure endpoints. If we move to the ecological impacts, the hazard acute versus chronic, and doesn't talk for aquatic, but not at all about air and soil. The LCA use talks about aquatic characterization factors, so at the soil level, it distinguishes between natural soil factors. On the side, we have a total of 20 endpoints, 8 for 7 for air, and again, these are on the scale of 0 to 100, which means can be compared quantity health scores. And lastly, chemical safety systems typically look at 2, flame and explosivity or reactivity. LCA does that, and the GreenSuite risk endpoints there with the quantitative to 100. When you move below the dotted line there and look at exposure elements, there are no exposure elements at all under the so air, excluding operations of use or amounts. Under use talks, the data is aggregated, so it's combined and composite. There are no toxic thresholds assumed in the LCA considerations. Hazard effects are aggregated, as I said. So, and the LCA also takes into account the simultaneous loading of the data as opposed to the which specific data, specific to chemicals, to process, to products. The form before, the hazards are reduced then by different constraints. So that could be the amount of concentrations used. So all of those exposure constraints reduce the hazard. And we can give you very specific risk effects then, impacts, but it can also impacts, as we'll show you. And it's specific to a time and place. It's not universal. It's not to a total population. It's related to a specific work area. And last thing then is that you look at the overall impact assessment, which is the bottom line. The risk, or I'm sorry, the hazard only theoretical worst case. And assumes that whatever you're exposed to as 100% of that material. Under LCA use talks, they are hazards, but they're combined. These are in the aggregation of the LCA analysis. Under GreenSuite, then you have this capability of risks per category for endpoints. So these are 3 paradigms that historically have been available to make product building product selection decisions.
Okay, so when you put it all together and you're trying to make select a specific material, of course you want to take into account a specific cost would take into account cost, performance, aesthetics, and from the environmental health and safety perspective, associated ingredients. This isn't an effort to try in terms of meeting my chain. That's expanding the EHS attribute to include application specificity and a risk basis in a life cycle.
To make sure everyone is on board with talk about their own risk, but in the context of the risk assessments that GreenSuite does, embedding here into the lifecycle assessment is defined as the chemical toxicity or hazardous effects that exposure constraints, as I said before. So there is this equation here where the toxicity and the exposure are both considered under risk, but under the hazard only, it's only toxicity. In about a medical research physician then continue to operate in the field of toxicology today, and that's that the dose makes the poison. So you have to have some sense of whether a material that has toxic concern. And there are lots of things in our that we eat. We eat foods that contain arsenic. Arsenic's a rat poison when it's in its concentrated form, because then it's not a poison at the extremely low levels in food.
Okay, so now whether all of the layers that we use here, these are the life cycle application and data layers and systems that we put together. This inventory, which you saw earlier on, I use Umberto Next Universal Lifecycle to build out the cycle model using EcoInvent LCI data, which of course everybody knows is an eco and applying the use tox, which flagged that there was a potential for risk. George, on the other hand, based Particleboard inventory, he information into his the CCA software, which access the GreenSuite database layers, which have all these different modules included. Put is in the format of a green grade report card. So we looked at what was flagged from the life cycle assessment as a potential for risk. We then incorporated results from the green grade report card, and we came up with a cohesive interpretation of what the real picture looked like at the use phase. George?
When we did these parallel analyses, for example, between the life cycle assessment and the risk assessment that Rebecca just showed, one of the things that became apparent to us was the inability of life cycle assessment to identify specific concerns, specific of materials that were being evaluated in the life cycle assessment. And the reason for those is listed in the box with the red box. First of all, their thresholds for toxic effects are not considered in a life cycle assessment. Of a safe exposure level isn't possible routine and risk assessment. The dose response in life cycle assessment is related to mass and linear matter, whereas in risk assessment, those can be very specific and constrained. The third element in life cycle assessments is the simultaneous exposure to all of the regards to the time or place, whereas risk assessment that can be very specific. And then lastly, the life cycle assessment assumes additivity of toxicity across all the effects and endpoints. And for example, classify factor in life cycle assessment, whereas in our analysis, 17 different endpoints for non-carcinogenic health effects. So we came up with these questions, driver for both Rebecca and I to continue these. And so the questions, we looked at the life cycle that she was reviewing. Are the mass-based and generic methods, are they sufficient? Do they give you enough information to select building in an informed fashion? Or a subset of that is, are the characterization factors in the life cycle assessment, are they sufficiently helpful? Third is the modeling used in use talks, for example, and is it applicable to the use phase, which is a significant part of the life cycle? Are aggregated human exposure impacts efficient indicators, or you need to have them more specific than the aggregation that you get out of LCA? And then lastly, the LCA data does not include dermal exposure is that critical to doing human health impacts? And in many building material applications, people are touching these different products. It is getting on their skin, might even be getting in their eyes. And so this dermal exposure would seem that it might be a significant consideration.
Okay, so the next 3 slides are going to deal with the underlying data structures in the database layer, because from the LCI perspective, and I come from a systems integration background, I was looking for how I could augment the existing data so that it would not limit the LCA, and or if we could integrate some of the risk factor information into LCA data. And you know, this is just basically, everybody knows how this works, integration of use tox into EcoInvent. Use tox has 3 factors, as George has gone over, for carcinogenic, non-carcinogenic, and total impact. And then in terms of media, there's water, soil, and air characterization factors that are mass-based, and they do have 2 versions, long and short-term emissions. So when you look at when you're building a life cycle assessment with EcoInvent data, and you'd be looking for, if I'm adding formaldehyde in my process model, then I would go, okay, I need to select the compartment air and air emissions high population for the manufacturing, if I have emissions that are being released to the air, and similarly for water and soil. So when I look at the actual formaldehyde emission data that I have from, I just took this record, it shows this is how global or how unspecific the data is. So I'm just looking at this on, okay, this is a place where there's a data gap, and I need to look a little bit closer at the data to make sure I'm providing the correct information. Okay, go ahead, George.
The data gaps, in looking at the parallel analyses, there were data gaps that became apparent here, and one of the first questions is what product in the life cycle is releasing formaldehyde? And remember, we're focusing on Particleboard, and the formaldehyde is the initial reactant. So what product, what phase is that being released?
And then, you know, is the building in Alaska or is it in Florida? Temperature, humidity, season, time of day, those types of things are going to come into play.
And our air exchange rate's important. The concerns with formaldehyde are predominantly inhalation, and so if that's inside of a building or outside, the air exchanges and the dilution factors that can become apparent from that. What is the impact on the decision process?
And in terms of when you're manufacturing a product and by the time you deliver it, there's going to be a delay, and that delay is going to be important to know in terms of what kind of, say, for example, free formaldehyde is still going to be floating around. So this piece of information is important.
And when you think of the use of Particleboard, and you're using it to make something else, it's usually including some sort of finishing on top of it. So it could have a coating or encasing of other materials. And what is that going to do to the overall life cycle assessment or a hazard-only assessment if you've got the formaldehyde inside a Particleboard sealed inside?
Okay, and then this was an interesting problem that I came across when I was building this out. Manufacturers of Particleboard are actually inserting what's called a scavenger resin, and that's the that we have in our inventory. And the scavenger resins are actually designed to capture excess formaldehyde. So how do I account for that when I do an LCA? And what if the scavenger resin has ingredients, which it does, that might flag a hazard-only assessment? So it's just an interesting problem, this last bullet item. And now we're getting into some of the specific different building product tools, the hazard-based assessment tools that are out there. The Quartz project is a collaboration between Flux, the Healthy Building Network, Google, and ThinkStep, and they have a database of what's called common product profiles for building products. It's their health profile is, as you can see down here, it's an aggregated hazard screen. by percent of total product weight, and it does exposure risk. So what they use is, as George described previously, on the paradigm, and they have, if it's orange, it indicates level, and so this is what Quartz offers in terms of for materials assessment when you're making selection. This is what you're going to see. So you're telling them that there's from one substance there's a high hazard, and that 86.73 of the rest of it they don't know, but they don't say at what phase. They do say it's manufacturing, but that's it. So that's a data gap that we identified. Now when you go over to the environment of the equation, you'll see that they have an environmental profile that's EC 2.1 method using different impact categories, and instead of using the traces, they replace CalTOX with detox human health criteria, and using the use tox results, they did go back and rely on the hazard list translator that's used by Pharos, and I believe it's used by Pharos, but used by Quartz. And they have also no installation and use phase. That to me was a huge data gap. So that's what we're trying to fill by risk assessment into lifecycle assessment. The other organization that I'm familiar with is the HPD Collaborative, the Health Product Declaration Collaborative. And this is an HPD, or Health Product Declaration of version 1 for a generic particle board based on the chemical constituents that George provided me with. And as you can see here, what we're focused on is we built it with beechwood dust. And even though the beechwood dust would not be free, it would be totally embedded inside of the particle board. It's flagged as a LT1, which is the highest risk, highest hazard. I gotta stop using that word risk. And it's carcinogen group 1. So that's the problem with the hazard side of the using hazard only for materials assessment. And George?
So if you look at the options that are available, the analyses that we've done for the particle board in this presentation are LCA using use tox, but the examples with the quartz that she just talked about could be LCA with just hazard only. We're also going to be showing you a GreenSuite only, and then ultimately the whole purpose of this presentation is what does it look like if we embed GreenSuite into lifecycle assessment, so we're using both tools. And the context is that generally as you move from left to right in this table, you have aggregation and generic information in any of the areas that are using LCA. So the first two columns are using that. The GreenSuite column has highly specific information about materials and formulations and exposures and impacts. And so when you merge those with LCA and GreenSuite, and the whole concept that Rebecca saw when she first saw the GreenSuite webinar was that by putting those together, you can have the activities and exchanges from LCA, but the quantitation of the and the specificity of the GreenSuite analysis that then starts filling in some of the data gaps that are inherent within LCA.
Okay, and so now we actually move into what we found out when we ran our, when we conducted our study. Let's see here. Okay, good. So in terms of when we put the model, I just ran it for this specific process. Again, we're focusing on the generic resin CR using the use tox assessment method. We go down the list of the different resins of the different inputs, the chemical constituents that are inside this. You can see, okay, we've got the high TU of comparative toxicity unit 10, and it's for urea that's being released to water and surface water. So I have these questions when I look at this information, and I say, okay, is the higher CTU score the highest risk? Yes, I guess so. what is the concentration of the urea in the water? And then from the other perspective, is it now I have to say, okay, if I'm going to look at trade-offs or I'm going to make a change in this formulation, is it preferable for me to release less urea to water than formaldehyde to air? So I need to add some context to this 10 CTU. And the only way I could do that is by proceeding with a risk assessment. So there was no ability for me to determine if 10 CTUs is bad, meaning is it toxic and how toxic. So there was no toxicity threshold for me to also refer to. George?
So now we're going to talk a little bit about how GreenSuite operates. How does it do a risk assessment and feed its results into LCA? And it starts with a database, not unlike the databases that LCA relies upon. But basically, the predominant data used here is the chemical database on the left. And we've been compiling this for the last 30 years from CCS. We have over 280,000 chemicals in it. In our green database, right in the center of this chart, we have 27,000 chemicals with highly detailed information that we'll talk about in a little bit. But the context then is that we want to do comparative assessments in a risk mode, an alternative. So we have different generic categories of chemicals here under the alternatives generics, so we can substitute. So one acid that's less green or one that's less green, and we can go to this and pull the data. Regulatory data for over 800 in the database, over 10,000 products, and the suppliers, the manufacturers for those products. The database that's behind. The second chart here, there we go, that's the one we want. This print is way too small for you to really see, so I'm going to basically large print. Can you scroll that up just a little bit?
No.
Right, that's fine.
Yeah.
I'll tell them what's there. They can see it when they look at it. But we start in this chart on the right-hand side. There are 44 endpoints that you can see there. You can't read the individual endpoints, but they start with water exposure and partitioning toxicity and long-term effect, for example, and they proceed down and acute and chronic health. This data for these 44 endpoints is information that we have compiled over the past 30 years on these 27,000 chemicals. And we use this data in doing the risk assessments for the Particleboard constituents, both the chemicals and the resins. And you'll notice across the top here, the sub chart is that we can use this for chemicals, for products, finished manufacturing processes, and that can be both input and output, and waste streams that are in processes. But we use these 40, and the way the system works is that it, or let's say it's in a product, then it goes into the database and pulls out the 44 endpoints for each of those 5 chemicals, multiplies those individual score 100% times the concentration of that product formulation, and then merges that data from right to left, so that you can get a water score, a soil score. Those are ecological score, and the ecological and safety to give you an overall, what we call a green grade. All of this table, all of this with numbers, for every place you see words and have the numbers in it, they will be on a scale 0 to 100. When we show you some illustrations, scores are less than 65, since 100 is perfect, is live, then we will show those numbers, so it's easy to pick them out. Next. We have a set. You'll notice that this one has 4. This is more close to think of in terms of life cycle assessment. For those of you that are in that, you can see it's in mass efficiency, factor usage, and energy consumption, bio-based content, process safety. These 24 endpoints are data that are manufacturing process, and basis that has to come from the manufacturing process specific and product specific.
Sorry,
Go ahead.
go ahead. No, just like intensity units, or they're derived numbers from a carbon or a water, something like that, or they may actually come from the eco database. You don't know what, so the manufacturer supplies these to.
Right. Okay. And then the next chart. So we have this at the engineering factor. So the question about GreenSuite, it is made up of 8 different modules. So one tool can't do it all. Here over on the left, where the first level is for the chemical product, and we can look at consumer exposure in the 2 blue boxes, or we can look at chemicals and products in their constituent in formulations, and you can see those use points. So as for the engineering, the one uses the 24 endpoints, and the 2 in the middle, the process and waste stream, use 44 endpoints. And the third level down here for procurement and acquisition is the supplier family tree, where we can do the same kinds of analyses on raw materials coming into the process and carry those results up into the other analyses for products and processes.
Okay, now we're going to merge risk assessment. Finally, here we go.
And so push this 4 phases of the life cycle. For the way that GreenSuite looks at it, assessment looks at it, in the sense that there is a design or pre-phase, there is a manufacturing phase, a transportation, storage, and usage, where you have a finished product, and then it's where, and that disposal can be include waste rated through the manufacturing or the phases. At the bottom of this, we've illustrated that in red there, the GreenSuite modules, and that's why one tool can't do it all. And so we have modules that are different phases of this life cycle, but all of the modules can come up with a score between 0 and 100. So we can compare those scores on a equal footing and determine which phase of the life cycle has the big concerns, then inside of that, and see what product or phase of the life cycle is causing that low score. And so results, and any of the words on this thing, but you can see the colors. And the thing I want to emphasize is that we're still talking about the Particleboard resin CR. These are the instance or with a score of less than 6 shows up in red. So you can see with reactants a lot of redness in this, and the overall score in this is a 64. So score here for the incoming the next chart. This is where we're now. We could have shown you report cards on all of them, and you couldn't read them. So now we're summarizing the data in this table. Reactants. The resin CR that we just showed you, example green report card, is at the bottom of here. There's lots of red. The right of the resin SU also has a red for ecological and health, but the other 2, the wax emulsion and red, they're all black. You can see then that this quantitation in determine where are the concerns in very specific portions of the manufacturing of the part. And when we look at further down, same RCR resins, what is the waste going to air? And you'll notice here that these scores, which you can see all of these numbers, they're very, very high. Everything's 100 except for the chronic health, which is a 99. And so it isn't confusing, is that those are identical for the waste materials. We have ethyl alcohol, melamine, melamine formate. All of them had those same exact numbers. Why would they be the same numbers? Well, you look at the ethyl alcohol is 1. Melamine's 0.009%. It's even lower at 0.002. formate is in there at 0.001. The reason those scores are so high is that there is chemical being released to the air. And if we switch then to the next phase and look at what's going to water, just to go back and compare to what about in the LCA analysis of this same CR going wastewater. And here that we're going to water, borax, potassium. Again, they're black, there's nothing red here. Most all of them are above 90, which is a very high. We generally consider that a non-90. The worst score overall is for urea, but you'll notice it's at a 42% of the material going into wastewater, whereas the borax, with there essentially is at. So by you bringing this quantitation into, we put a perspective, because when analysis and showed that urea value of 10, she didn't know what that means. This analysis tells you that this is 100 being perfect. So even though you have urea, it's not creating a risk. The next chart then, bring report card, and this is for the outgoing now. Now remember how the reactants work from the incoming. Well, you still have a few red lines up. I think there are 5 total, but there's significantly less red in this on the incoming. For all green grade over here on the left, at 64 reactants. Here is outgoing resin C. Now again, in the same format as before, we're looking at the total formulation for Particleboard itself. So it has wood in it, and then it has these wax emulsion and 3 resins. The lowest resin and resin CR, the lowest score, it's an 87. It's not a bad score. It's a score. And so the context here, see what is the score for each component in particle in contrast to the overall particle board. Material, here's the green report card for the finished particle done now. And you again, it's hard to see the overall green grade. It's a 98. So for the in CR, we had a score. For the outgoing resin CR, we have, for the finished particle board, we have a 98 score. And think of this used in something like furnace, going to have a coating put over. So we've significantly minimized the concerns related to the particle board over its life cycle.
And again, if you look at this versus a hazard-based system, it really provides you that it will cause this, exposure scenario.
And this overall now, here's a graphic of it. So on the high column showing that formaldehyde, when it's considered as 100% raw material going in as a reactant, up as 70% here. But now when you've reacted them, the output materials from those initial reactants, the scores have dropped down significantly. Moved to the surface resin and onto the cured at the far side. Remember that particle board was a 90. So you can see that across the different phases of the production process, you are attenuating what was high hazard, so that it has no risk of concern of the life cycle when you're actually.
Okay, so now we take a look at how we've expanded these to embed risk. You can see that now to get very specific information that is more credible, and it's much more useful for architects and designers who are making these material selections when disciplines blended together. And we were able to slide in talking about what would complete material assessment. You can see that we really do with risk and LCA. So that's why we have the double check marks to really emphasize that point. We've got environmental impact information. We've got very site and application safety and health information. And we finally have the use phase and information for the specific product. Now, in terms of integration strategies, we could, again, I did to keep it simple. All right, so going forward, it can be very successful doing things as is with no app data layer component build on top of things. If we were going to use LCA only, we'd have to look at addressing how system boundaries and residues and things like that. If we wanted a tighter integration between GreenSuite and any other LCA software, such as some integrated tool set that's build some sort of data or application layer, but it's mainly a software and database problem, just like any other integration issue that you run into in any other type of software. Some of the challenges.
Yeah, so now that we've finished the presentation on the Lifecycle assessment, strengths and actual report cards and data generation from the risk assessment, all isn't solved. There are some challenges remaining. The first challenge is the acquisition. Time ago, but that data has to be accumulated in order to do the risk assessment for every stage of the life cycle. In addition, we have to know the uses so that we can be use specific and take into account the right exposure information. The tier of decreasing the subjectivity in LCAs and increasing is a challenge because that's not innate within that analytical procedure. We see the value of this, having done it now for the complexities of a particle board, but in order to do this in a more cost-effective way, then the process needs to be integrated or automated. And then lastly, the final challenge is selling this to you either comfortable with risk assessment or comfortable with life cycle assessment, but don't know the other option. And that's what creates the new paradigm by merging these two together. So the conclusion, the first conclusion is that we have been able to demonstrate here that integrating risk and life cycle assessment is currently a technique that we could do right now. We have all of the capabilities and the data that we need, the processes.
Okay, an enhanced environmental health and safety phase incorporating a risk profile definitely fills in the gap that neither LCA with its current impact assessment methods or hazard-based assessment methods combining those two.
And integrating the risk assessment data into the life cycle assessment shifts the paradigm now away from the misleading hazard only conclusions.
Okay, and now we just have very specific data to the for the application of particle in the specific building scenario. So if it's going to be used, to know that it's going to have a barrier on it, or sure it's going to have a coating on it. So we've got that specific site, product, and use exposure data.
By merging in the risk each of the stages of the life cycle, you can actually look at ecological health and safety risks, and that they can be even take detail levels of those 44 endpoints that we talked about.
And basically, when you have more information, it goes back to the old, the more you know, you can obviously make better decisions.
So we're hoping that building designers that may be on this webinar realize that by using the best science from both LCA and risk assessment, they can now make quantitative and better building material selection decisions.
Okay, and as indicated by the last few slides, George and I have this in our spare time, and in order for us to get a tighter integration, we will have to start seeking some funding options. So thank you for your time.